So, hello. Today we are going to learn about the strongly connected component. So, first we have to see what strongly connected component is. Strongly connected component, or SCC, is the set of vertices in which each vertices can be reached from any other vertices. Means any other vertices are reachable from any vertices in that set of vertices. For example, you can see in this graph, suppose this is the graph. In this we have two sets of strongly connected component. One set contains of 1 and 3 vertices, and the second set contains of 2 and 4 vertices. See, 1 and 3 vertices. From 1 you can reach 3, from 3 you can reach 1, and of course any node can be reached from itself only, because itself it is the node and it can reach itself. See the 2 and 4 set of vertices. From 2 you can reach 4, and from 4 you can reach 2. Similarly, in this graphs, the set of vertices which are strongly connected component are 3 and 4 only. 3 and 4. From 3 you can reach 4, and from 4 you can reach 3. If you will observe, there are no any strongly connected component, because from each node it can't be reached from any other node. So this is what a strongly connected component is. So how we are going to find out the strongly connected component? We will be seeing its implementation. So for that, in this we use two DFS function. First DFS function will calculate the order in which we have to call the second DFS function. Means it will store the we will have one order vector. In that the vertices will be stored in some order, and that order will be the increasing order of out time of nodes. I will be explaining what the increasing order of out time of node is, and in the highest vertices having the out time will be called first in the second DFS function. So second DFS function will be called in the with highest out time of nodes. So how we will be calculating in the first DFS function? We will be calculating the order in which we have to call the second DFS function. So how we are going to do that? See, this is the common DFS function that we have studied till now, and for pushing any node in increasing order of their out time of node is the time at which we leave any vertices after its execution is already completed. We will be just pushing that node in that. So whichever vertices will be completed first, we will push that. So the last element will contain in the order vector will have the highest out time of that. Out time will be of that node. Let's trace this code. Suppose we call a DFS 1 from the main function. DFS 1, it will see, we will visit the node. It will see its child. 3 is its child. Is it visited? No, 3 is not visited. See the code here. If we visited child, 3 is not visited, then we will call DFS of its child. Now it will go to 3. It visited of 3 will be marked as 1. 3 will see its child. its child is only 1 and it is already visited, so its execution has till here, it will not come here, so it will be pushed back in the node. 3 is pushed back, so DFS 3 is completed. Now it will come to DFS 1. DFS 1, till here DFS 1 was completed. It will be pushed back in the order array. So 1 is pushed back. And we will return to the main function. We will check 1 is visited, yes. 2 is visited, no. So we will call DFS of 2 from the main function. We have called DFS of 2. We will mark, now it will come in this DFS function. Visited of node equal to 1, visited of 2 equal to 1. It will see its child. 4 is its child and it is not visited, so it will call it DFS of 4. It will visit the node first, 4th node. Now 4 will see its child. Since the child of 4 is only 2 and it is already visited, so it will not come here. Ordered, it will be pushed back in the order vector. So 4 will be pushed back. After that DFS 2, till here DFS 2 was completed, and then 2 will be pushed back. So this is how, and all stack is empty, so it will return to the main function. So this is how we have calculated the order vector. The work of our one work is completed, that we have to make one order vector in which we will have the increasing order of the out time of node, out time of nodes. So we have stored that. Now we will be using this order vector in second DFS function to call the vertices in the decreasing order. Means first we will call the second vertices, then in 4, then 1, then 3. If it is not 4 is not visited, then 4. If it is not visited, means we will go in reverse order of the order vector, calling the DFS 1 in the transpose graph. What the transpose graph is? This is our adjacency graph that we will be given, and we have to create our transpose graph. For that we have to just reverse the edges. How we are going to reverse the edges? In the adjacency list, how we are doing that? We are pushing adjacency A dot push back B. Then in the transpose list we will be pushing adjacency transpose of B push back A. This is how we will be able to reverse the edges and create the transpose graph. So we will be creating this transpose graph, and we will calling this DFS function in this order that we have created. So second DFS function will be called in the transpose graph. So see the transpose graph and see the order. Two things that we have here, and we will be calling the DFS function, DFS 1 actually, second DFS function. So in the main function we will be start reversing from the reverse direction. So DFS 1 of 2 will be called. Okay, DFS 1 of 2 will be called. Visited will be marked as 1. Visited of 2 will be marked as 1. We have marked it. It will see its child. 2 has a child 4. So it will call DFS 1 of 4. DFS 1. DFS 1 is the name. Here also DFS 1. DFS 1 of 4. We have called. 4 is will be also marked as visited. Now it will traverse its child. 4 has the only child 2, which is already visited, so it will not come here, and we will push back the node. We have 4, we will push back 4, and the work of DFS4 is completed. Then DFS2, till here DFS2 was completed. It will come here, and 2 will be pushed in the strongly connected component node. So 2 is pushed back. Now stack has become empty. It will return to the main function. In the main function, it will check whether 1 is visited. No, 1 is not visited, so it will call it DFS of 1. So DFS1 is called. It will see its child. First it will mark visited. It will see its child. 1 has a child as 3, and it is not visited, so it will call the DFS1 of 3. Now 3 will see its child. 3 will be marked as visited. 3 will see its child, since the child of 3 is already visited, so work is completed, and we will be pushing that node in the SCC vector, that is strongly connected component vector. While we have returned in the first half, when we have completed this part, then we can use this strongly connected component vector as this is the strongly connected component graph. 1 and 3 is in the same. We have get this one. 1 and 3 is in the same strongly connected. We have got this one. So we will, and 4 and 2 are in the same. So we have got the 4 and 2. We can use this strongly connected component vector in any way, and then we will clear it. And the next we will be pushing the 3. 3 has been completed, and then 1 has been pushed, and then it's completed. Then we can use, while return to the main function, while returning to the main function, SCC as 1 and 3. We have got 4 and 2 in the first call from the main function, and 1 and 3 in the second call. So this is the way of finding the strongly connected component. These are the two DFS function. This is the order vector, this is the visited vector, and the SCC vector. So this is the way. You can try this in the test case 2. We have got the adjacency list. The transpose graph will be this one. This one will be its transpose graph, and adjacency list is there. We will be creating the order will be come to this one, and we will be calling the DFS, second DFS, in the reverse order of this order vector if it is not visited, and we will be pushing it in the strongly connected component vector. So this is the way, and we will be solving one problem of port Ceph in the next video, and by using the same concept. So hope you have understood. Thank you very much.